A 90,000-pound fighter jet sits motionless on the deck of a floating city made of steel. A ship with no runway, no margin for error, and only 300 feet of space to launch. In just 2 seconds, that jet will accelerate from 0 to 165 miles per hour, slammed skyward by forces so intense the pilot is pinned to the seat. There is no safety net. One misfire risks 4 lives and a $120 million aircraft. But this isn't fiction. It's routine, repeated hundreds of times in every deployment without fail. This is the launch cycle of the U.S. Navy, violent, precise, and utterly unforgiving. And it didn't start here. Launching jets from a moving runway in the middle of the ocean isn't just dramatic. It's a real engineering problem. One the U.S. Navy has spent decades solving, improving, and refining. In the early days of naval aviation, steam-powered catapults made it possible to launch aircraft from short decks. They worked by building up high-pressure steam, releasing it into a piston system, and slamming a shuttle forward to pull the aircraft with it. The idea was simple. The machinery was anything but. These systems were heavy, difficult to maintain, and rough on the airframes they launched. As aircraft became faster, heavier, and more specialized, the limitations of steam became harder to ignore. Steam systems couldn't easily adjust force between aircraft types, and they lacked the fine control needed for more delicate payloads, like drones or surveillance platforms. That's where the Navy introduced a new system, the Electromagnetic Aircraft Launch System, also known as EMALS. Instead of pressure, it uses electricity, and instead of brute force, it uses programmable control. At its core is a linear induction motor, essentially an electric motor unrolled along the length of the deck. Using a series of coils, it creates a moving magnetic field that accelerates a carriage, called the shuttle, with extreme precision. That shuttle is what pulls the aircraft. This allows the system to launch everything from heavy fighter jets to lightweight unmanned craft, all on the same track, tuned in real time by software. On the surface, the launch still looks violent, but what's happening underneath is silent, smart, and scalable, built not for show, but for the future of naval warfare. Before a jet can leave the deck, dozens of actions have to happen in perfect order. Some of them visible, most of them not. The process begins below deck, inside the control room of the launch system. Operators power up the system's energy banks, which store electricity in massive capacitors. These capacitors don't release energy all at once. Instead, they deliver it in tightly controlled pulses, sending power to a network of electromagnets embedded along the launch rail. Up on the flight deck, the shuttle is guided into position and locked to the front landing gear of the aircraft. This metal bar, called the launch bar, is what physically pulls the jet during takeoff. Once the jet is in place, a holdback bar keeps it from moving forward. This bar is designed to snap free at a precise force, allowing the aircraft to release only when the magnetic field reaches the exact acceleration target. When the launch signal is given, power flows through the coils in sequence. Each one activates just in time to push the shuttle forward and then shuts off. This creates a wave of electromagnetic force that moves down the rail like a ripple, driving the shuttle and the jet with it down the catapult track. Unlike steam systems, which apply force more abruptly, the Electromagnetic Aircraft Launch System builds acceleration more gradually and smoothly. This reduces stress on the airframe and gives operators more flexibility based on the weight and type of aircraft. From start to finish, the launch lasts just over 2 seconds. But behind those 2 seconds is a precisely timed chain reaction of software, energy control, and human oversight, all working together to send 90,000 pounds of jet into the sky. The most impressive thing about the Electromagnetic Aircraft Launch System isn't its speed, it's its precision. Launching a jet off a ship isn't just about brute force. It's about applying the exact right amount of force at the exact right time, based on the weight, drag, and thrust profile of a specific aircraft. Too much acceleration and the airframe could crack. Too little, and the jet might stall mid-air. That's why every launch begins with a software calculation. The system takes into account the aircraft's weight, weather conditions, wind over deck, and mission payload. Then it generates a unique launch profile, a custom power curve designed for that exact jet in that exact moment. To execute that curve, EMALS relies on thousands of feet of copper coils and power converters. These aren't simply turned on and off. They're pulsed in sequence, controlled by microsecond-level timing systems that adjust in real time. Each coil energizes just long enough to continue the acceleration, then immediately shuts off to prevent power loss or overheating. It's not just technical, it's surgical. This fine control also allows for much smoother launches than older steam catapults. Instead of a sudden bone-rattling jolt, the pilot experiences a smooth buildup of force, one that ramps predictably and reduces the wear and tear on both the aircraft and the pilot's body. But precision doesn't mean simplicity. Dozens of subsystems monitor energy levels, temperature, timing, and current at every step. If even one component lags or surges, the launch can be scrubbed in an instant. It's why every successful launch is not just a victory of hardware, but of coordination between engineers, deck crew, flight ops, and software that all have to speak the same language, perfectly, every time. No matter how advanced the system is, it doesn't run itself. Behind every launch is a network of people whose timing, communication, and trust hold the entire operation together. On the flight deck, it starts with the green shirts, the catapult crew. These are the sailors responsible for hooking the shuttle to the aircraft, checking launch alignment, and signaling readiness. Each one has a specific role: weight checking, shuttle positioning, holdback verification. They operate in deafening noise, under pressure, just feet from jet intakes and exhaust. Overseeing the launch is the shooter, the officer who gives the final go. With a single hand gesture, the shooter triggers the sequence that will release stored power and accelerate the jet off the deck. That moment is a blend of authority, instinct, and nerves, because once that signal is given, there's no pause button. For the pilot, the experience is equally intense. The aircraft goes from standstill to flight speed in just over 2 seconds, generating over 3 Gs of force. The jet doesn't gradually lift off. It's launched. One instant, it's locked to steel, the next, it's airborne. Most pilots describe it as a shock to the system, violent but clean. The launch pins their body back in the seat, forces vision to blur, and demands total focus. And yet, they're trained to scan instruments mid-launch, already preparing for the first turn, the climb, the mission. Below deck, technicians monitor power systems, capacitor temperatures, and the real-time timing curves of the launch. If anything deviates, they call for a stop. There's no shame in canceling a launch, only in getting one wrong. In the end, the system may be built on electricity and software, but it runs on human precision, courage, and trust. To most people, EMALS looks like cutting-edge innovation, a futuristic upgrade that replaced steam with something sleeker, faster, and more efficient. But to the Navy, it's something more important: reliability at scale. The electromagnetic aircraft launch system wasn't designed just to impress. It was designed to launch aircraft thousands of times per deployment, in every condition imaginable, from calm seas to combat theaters, day or night, with minimal downtime. And that's where the real brilliance lies. Because steam catapults, while powerful, had limits. They needed time to build pressure. They strained under heavy usage. Their mechanical systems wore out quickly and required crews to be constantly repairing, tuning, and monitoring subsystems. EMALS shifts that paradigm. It delivers power on demand. It requires fewer moving parts, and it allows engineers to fine-tune acceleration curves without physically modifying the system, just by adjusting software. That flexibility means the system can evolve. As new aircraft are added to the carrier's air wing, from manned fighters to autonomous drones, EMALS can adapt without needing to be rebuilt. In short, it's not just modern, it's modular. And that makes it not only more efficient, but also more future-proof. But routine excellence isn't just about technology, it's about tempo. EMALS allows the carrier to launch more aircraft, more often, with fewer delays. That tempo creates air superiority, a continuous cycle of launch, recover, refuel, rearm, and repeat. And in modern naval warfare, tempo wins wars. In a global theater where conflicts can emerge overnight, the U.S. Navy's ability to put aircraft in the sky from anywhere without needing a runway is a unique strategic advantage. And EMALS is a key part of that capability, because it's not just about launching planes, it's about launching air superiority, fast enough to intercept threats, flexible enough to support any mission, and efficient enough to maintain 24/7 operations if needed. Other nations have aircraft carriers, but few can match the scale and tempo of American operations. That's what makes this system so valuable. It multiplies capability without multiplying size. A carrier equipped with EMALS can cycle more aircraft per hour with less wear and tear and more adaptability to future airframes, including next-gen stealth fighters and carrier-launched drones. And in contested waters, the South China Sea, the Persian Gulf, the Strait of Hormuz, that kind of performance isn't just useful, it's decisive. It's what allows the U.S. to respond quickly, project strength without firing a shot, and maintain stability through presence alone. And as global naval competition increases, systems like EMALS aren't just tactical tools, they're strategic statements. Statements that say, we can be anywhere, we can launch anytime, and we're ready now. It's easy to watch a jet launch from a carrier and focus on the spectacle, the roar, the speed, the violence of motion. But behind that 2-second burst is a century of problem solving, thousands of hours of engineering, and the synchronized actions of dozens of people, all trained to operate with absolute precision in one of the most complex environments on Earth. The electromagnetic aircraft launch system isn't just a technological leap. It's a reminder that innovation doesn't always announce itself with fanfare. Sometimes it hums beneath the surface, quieter, cleaner, more efficient, doing its job with unrelenting consistency. And it's only the beginning. As the Navy integrates more unmanned aircraft, stealth platforms, and next-generation fighters into its carrier air wings, systems like EMALS will become the baseline, not the cutting edge. But that's the point. In naval aviation, excellence isn't about breakthroughs that happen once. It's about breakthroughs that can happen over and over again, on demand, without fail. Because when a 90,000-pound fighter jet hurls off the deck of a ship, what you're seeing isn't just a launch. You're seeing confidence, projection, control. And somewhere, in some corner of the world, you're seeing a message received.